I used to do this. I would bring in all the materials to make a peanut butter and jelly sandwich. And maybe people have seen this before, but like you ask students to give you a step-by-step instructions of how to make the peanut butter and jelly sandwich.
With brushing your teeth.
Yes. Okay. And so then they start out so generic in how they explain, like, tell me, what's the first thing I do?
Make the sandwich.
Right? And you're like, well, okay. And then you can finally get them to be like, put the peanut butter on the bread. So I take the entire jar of peanut butter and I set it on the bread. And I'm like, that's literally what you told me to do, right? You're not being very precise. So then you can start to introduce this language of like, in math, it's the same thing.
Aaron, do you want to introduce yourself
Absolutely.
to me?
To you?
Who are you?
Sounds good. I'm Aaron Kugler. I have just recently joined NWEA. I joined in March, actually, and I'm on the Content Connections team. So a lot of what our team does is kind of connecting products and solutions across the enterprise, which now includes HMH, obviously. And so we take a lot of time and energy in looking at research and making sure everything we do is research backed and best practice in the classroom, both on the instruction side and then obviously the assessment side with all of that NWEA does. So it's been a lot of fun. It's been a ride so far. I can't believe that like I get paid to just be nerdy about math and research crazy things and then obviously come to great places and talk about them. I got to present here at Fusion. So yeah.
What was your presentation?
My presentation was actually not on math. And so it was, it's my first time, but it's totally okay. Like, got to get your foot in the door. And then I said, next year, I will come back with a math topic.
Okay,
Don't you worry.
I can't wait to go. What is one thing, as your background as a math teacher, what is one like mathy concept that if you could give to teachers to empower them to be a better math teacher as they head into the next school year, or maybe they just head into Monday, what would it be?
That's a pretty loaded question, right?
Yeah.
And it's hard to pick just one thing because, and there's a lot of things I could focus on. My kind of, I guess I would call it a soapbox. I always say I have soapboxes and rants in the realm of math education. I am really a stickler for precise language.
In math.
And that to me gets me like really to the core of where I see a lot of misconceptions coming out in students when things are explained in ways using terms that are not precise. And so let me give you an example of this, for instance. So imagine you're in a second grade classroom, right? Let's say we're learning subtraction and we're playing with this word problem and the students, maybe a couple of the students are having a hard time figuring out like how to set up their vertical equation. Like how would I, take the values from the word problem and set them up in this way so I can do the subtraction? Maybe some of them are mixing up the order in there, which one is being subtracted from which one, right? And so in some of these situations, I feel like you almost get stressed to come up with a way to like explain it to them. Like, how can I say this in a way that like makes sense to students? And then an imprecise piece of language will come out of your mouth as the teacher. Yeah. And you don't realize you've sown the seed that could lead to misconception later on. So a teacher might say something like, remember, in subtraction, we always put the bigger number on top. Well, that's problematic for a couple of reasons, right?
First of all,
yeah, here we go, right? Like when they get farther down the path, in subtraction, we don't always put the bigger number on top.
There are negative numbers.
You can, in fact, take a larger number from a smaller number. So as soon as they break into middle school and integers and everything like that, automatically that rule just goes out the window. It expires for them, right? The other thing is, and many more people may not have caught this, is that bigger is actually an imprecise term in that sentence because when we're talking about numbers, we're talking about magnitude. We're not talking about size. Numbers don't actually have a size. They have magnitude. So in that situation, a more precise term would have been greater, right? Like if we're talking about the greater number in that situation, when we're talking about numbers, it's greater than less than. If I'm talking about size, maybe I want to write it bigger on my page, right? And we could
oh my gosh,
we could exaggerate that. I used to do that with kids too, right? They're like, well, the bigger number. And I'm like, these two numbers are the same size. They're like, that's size 12 font. Like there they are. They're the same size. What are you talking about, right? Like pushing them to use a more precise term that's kind of nested in the topic that we're discussing and exploring is the goal.
Oh man, how do you help math teachers catch themselves on this kind of stuff?
There's so many things to it, right? And you almost have to spend time like thinking about math yourself, right? And watching other people talk about math and being in discussions with your colleagues about math and observing great math teachers to see the way they explain things.
What do you mean by great?
Great math teachers?
Is it a greater number?
Oh, that's true, right? So many different definitions
I'm just
of great.
picturing like your colleagues and you being like, catch me when I'm imprecise. I'll catch you when you're precise.
Right.
And then you guys are like, everyone's just like, maybe
do I call you out on
Yeah.
that one? No. So, and there's another one I was thinking of. So fifth grade, I love teaching fifth grade math. But one of the things that drives me nuts, just in general, I think because the standard lends itself toward this language, is if you think about another one of those rules that comes up, that is a thing, is when we're talking about powers of 10.
Don't you say it.
I'm going to say it.
Don't.
So if we multiply by 10, that's the same as...
No, it's not.
Adding a zero. Okay.
If I add 0 to anything.
If I add a 0 to something, I get the same value. That actually has a name in mathematics. That's called the identity property of addition. Because any number plus 0 is itself. Like that's what helps us understand the relative value to other numbers. There's an identity property of multiplication. We can dig into that even more. But when we're talking about multiplying by 10, we're not adding a 0, right? And so a lot of times when we introduce that topic, then it's like, okay, kids can memorize this rule. Like, great, I just add a 0, just put a 0 on the end there, right? And then not 2 lessons later, because we deal with whole numbers first, and then we're going to jump into decimals. So what happens when in the lesson where they were looking at the number 126 and they added a 0? Great, yeah, 1,260 is 10 times greater because they added that 0 to the end. But then they get into the decimal lesson and it's 1 and 2600ths, 1.26.
Right.
They add the 0 there. What happens?
Nothing.
Nothing happened. You didn't change the value of that number, even though you added your 0, right? So
you really revealed the 0 that was already there.
Exactly. You're just highlighting that there are more place values.
Yeah.
And so automatically,
I'm seeing that we need to like write stuff on the screen to help people follow. Like we need like a whiteboard here.
You know that GIF of like the lady that's sitting there, like all the math is moving behind her. Like,
isn't it Julia Roberts? That lady.
What movie is that?
That lady.
I wonder if Julia Roberts understands the math.
She probably does.
She's
Julia
probably
Roberts.
really
She's Aaron
great
Brockovich
at it.
Mm-hmm. Well, whenever I say when I was teaching 6th grade remedial math, I would say, and I don't think that now that I'm like,
oh, now you're second guessing yourself.
No, I think
don't treat me as the expert because I trip up all the time.
That's okay. Okay, well, I think I'm about to make a confession, maybe that it is that I was using imprecise language, but I was saying we do not add a 0. We, in multiplying by a power of 10, move the decimal.
Okay.
But now I'm like, well, moving the decimal could be termed a little imprecise.
Right. And that's
probably better language than adding a 0.
It's like a half step better,
oh,
right?
God.
Because then
Only half.
Now you just split it into 2 rules because moving it to the right is one rule and moving it to the left is a different rule.
Yep.
And really, if you're just moving a dot on a page, that's kind of arbitrary.
Yeah, I know. You would just be that troll that was like, oh, you want to move it? Okay. And you would like move it to the corner.
Exactly.
Yeah.
Exactly. And I would challenge teachers to do that with their students.
Right.
I used to do this. I would bring in all the materials to make a peanut butter and jelly sandwich. And maybe people have seen this before, but like you ask students to give you a step-by-step instructions of how to make the peanut butter and jelly sandwich.
With brushing your teeth.
Yes. Okay. And so then they start out so generic in how they explain, like, tell me, what's the first thing I do?
Make the sandwich.
Right? And you're like, well, okay. And then you can finally get them to be like, put the peanut butter on the bread. So I take the entire jar of peanut butter and I set it on the bread. And I'm like, that's literally what you told me to do, right? You're not being very precise. So then you can start to introduce this language of like, in math, it's the same thing. If you're not being precise with how you're explaining things, how could you justify your thinking to someone else? And how can you critique someone else's thinking if you don't communicate using those same precise terms?
Because we're using, we're filling in blanks that we didn't know we left blank.
Right.
And like, I'm imagining that this can be extrapolated into so many places in education.
It absolutely does. Because if you think about the ways that we want to train students beyond mathematics to kind of look in and find bias. Let's say if we're looking at the news, right? How can I tell if an article that I'm reading is valid and accurate and up to date and make sure that there's bias in there that I can recognize and maybe see both sides of and perspective? Like all of this comes from an ability to critique the reasoning of others. And there's a reason that's a standard of mathematical proficiency.
Right.
Because we have to really focus on the language we're using to explain the things that we're doing.
Right. I have to know what you're talking about, make sure that you and I are on the same page about what they're talking about.
Yeah.
So that we can triangulate and consider it. I'm thinking about, I just came from an amazing session about multilingual learners and how essential precise language would be in their instruction.
Well, because so think about from the perspective of a multilingual learner, English is their second, third, fourth language.
Right. Full of idioms. Full of imprecise language, just period.
Beyond that, math is its own language, right? Like we're trying to teach them all these contexts, and they're constantly like code switching. They're trying to figure out like what are all the meanings and all these things. And then I throw the word bigger at them. And then they sit there and go, Mr. K, that 6 is not bigger than that 5. They're the same. What are you talking about, right? And it's like, oh, buddy, we're talking about magnitude. Remember, we talked about that word. And that's why I use like some of these nicer words like magnitude, connecting to a bigger idea of mathematics, right? Because if I can introduce a new topic, and yes, there's new vocabulary words we'll have to learn and understand, but if I can draw it back to, remember, guys, this is all about place value. This is all about understanding the value of numbers. And what is that called? We call that magnitude, right? So if we can bring it all back to that, then they kind of have this anchor every time we jump out to a new piece of terrain that they can kind of explore. So, gosh,
and I'm thinking about that like language learner that's just trying to remember the difference between like bigger, fatter, longer. Like they're like,
right?
Wait, okay, I'm working with a number line. Now we're talking length. Like, wait, okay, bigger. Is it to the left or the right? There's just so many things
so
to
then what
hold
do we
in their
do?
head.
What do we do as teachers when that happens? We're like, okay, well, here's what you got to do. If it's length, we're going to use the word longer. If it's weight, we're going to use the word heavier. And then we give them this list of like 20 rules for this situation, right? And we do kind of do this in life. Like that's part of the theory of how we learn is we have to experience things and we kind of develop our own theory of how it works, and we have to test that.
Yeah.
But if we treat math as like this long book of rules, we'll never get there, right? Like, because students are constantly having to sit there and go, wait, I remember I have to move the decimal.
And we want them to have dialogue with us. We don't want them to police their own language. We want them to be chatty in our math class.
Absolutely. And I don't want you to be so fixated on like what you're doing with that decimal that you forget to zoom out and go, but what's the value of that number relative to where we started, right?
It's like striking this balance between having precise language with our kids while not kind of like over paralyzing them about using it so that they're still chatty. But I think that maybe the one takeaway teachers can have is that I have to model that precise language.
Oh, 100%.
I need to hold myself to a little bit of a higher standard than I troll my kids for it.
Right. Absolutely. And catching yourself when you're in person. That's like the best thing you can do in the world. And I've always been a firm believer in like failing publicly in front of the students and owning it. Like, oh my gosh, I just said bigger. I told you guys.
Why is that a problem?
I told you guys I shouldn't use that word. And I used it again. Next time you guys call me on that. Right.
Right.
And then I think there's a secondary piece that's like, give the ownership to the students themselves. Like I liked to create, when I taught, a classroom where we're all mathematicians, we are all going to critique each other's reasoning. And I would almost let the students be the ones coming up with those theories. Instead of me saying, get up there at the beginning of the lesson like, okay, kids, powers of 10, here we go. When you multiply, this is the rule. No. Let's explore some of the situations. Do you see a pattern, right? Like in what's happening with these values. Can someone explain this, right? Like someone theorize. Why not use the word theory, right? Mathematicians get to theorize.
Yeah.
Why don't students who are mathematicians get to make theories? So we'd literally build theories, and then then the students all look at you, right? And they're like, is he right?
Mm-hmm.
I don't know. Is he right?
Right.
Like, that's for the community to discuss and figure out and make them poke holes in it. Can anybody find an example that doesn't work with that theory?
Or can anyone take the definition that so-and-so just offered, which was amazing and brave, and find one way to upgrade the language to something more precise?
I like that word too, right? Like we're trying to get to that like meaty statement about mathematics.
Pure statement. And it's hard.
Exactly. But once you get there, what a like relief for the whole room almost like relaxes a little bit.
Right.
Like we just did math, guys. We just did math, and celebrate it and put it up on the wall.
And we're all alive.
But I remember sitting in some of these classrooms with these kids and being like, that is phenomenal. I can't believe we just did that. You know what we're going to do? We're going to call that Liam's theory, like write it up on the wall for the rest of the year. It doesn't matter that it's, the commutative property, like whatever it is. Liam figured it out first and we built it into this great thing. That's Liam's theory. That's exciting, right? Like, and then later they can kind of just, reassociate it to what the mathematical property is. But because they claimed it themselves, they owned it, and they used the language to describe it properly, there's just so much more power to that they'll remember for far longer than
and
if I
that
just...
becomes like a big winning moment rather than a tired old dusty book that we're exploring old guys' ideas.
Exactly.
So if I'm a teacher and this is kind of blowing my mind and I'm realizing like, yeesh, I don't always do this. Or if I'm a teacher that's like, I've been doing this for forever. But I mean, if you are like Monday morning teacher wanting to go in and make some kind of change, or maybe just introduce this concept to students, do you have like a fun hook or a thing to look at that you would suggest?
Right. So there's a lot of power in monitoring when you're giving kind of like shortcut language. Be careful in those situations. And I used to say it like, and I've done some like professional development with teachers on this. And I called the session, watch your mouth. Like, be very careful when you're trying to just explain something quickly and concisely. And it's going to hit two groups of your kids most drastically. It's going to hit the advanced learners because they're the ones who kind of grasp that math quickly. They might even come up with the shortcut themselves. Right. And they'll have that like language of just like, oh, this is all you have to do, Mr. K.
Oh, that's so frequent.
Just so easy, right? Like there it is.
And
I'm like, ooh. Yeah, well, don't say it to the rest of the class, but at the same time, also, you're not really getting it if you summarized it so concisely that you used imprecise language, right? So it's going to affect those advanced learners, but then on the other end of the spectrum, my kids who need support, right? It's going to be detrimental for a lot of them if the first thing they can latch onto that makes sense out of your mouth is imprecise about that topic. It's going to take that much longer to unpack it for them and really try and figure out how they reason with what you just said. So,
what I'm hearing that I didn't hear when we first started this conversation is that imprecise language leads to shortcuts and which directly sabotage the deep conceptual understanding
that we're all going for. Like, it's almost counterintuitive, right?
Yeah.
Like, wait, the language I'm using to get at the conceptual understanding
Why do my kids not have
preventing me from not getting to the conceptual understanding, right? And that's like the fatal flaw of advanced kids, unfortunately, is like they get rushed into this system where it's a race and it's like, ooh, I'm so advanced, I'm so fast. I can like do things really quickly computationally. But then is my teacher pressing on me to say, wait, are you justifying that correctly? Like,
oh my gosh.
Explain your thinking. Go back. Can you show me another way to say that? Can you show me, like, because I don't have time, because I'm working with my struggling learners, or like whatever it is in that moment, there's kind of this situation where those kids don't get the attention they need to really build a more robust conceptual understanding of the topics we're talking about.
They're just like on like super greasy skis.
Because they got the easy one, right? And it's like, well, man, if they get to the end of 5th grade and they can, multiply like this, we might as well just throw algebra at them.
They are clearly
right?
understanding it.
Exactly. Because as soon as we get to middle school, it's not about computational fluency anymore. It's not about how fast you can spit out your facts. I mean, any middle school math teacher is going to be like, it'd be nice if they knew their facts, right?
Yeah. Well, that's just about reducing their cognitive load.
Exactly.
So that they can do that more advanced thinking.
In that mathematics. But as soon as you get into proportional, like the world of proportional reasoning, oh my gosh, if you can't explain what you're talking about and understand how two values change in relation to each other, you're done. Like,
if we added a 0 to one of them.
Ooh.
And then added a 0 to the other one.
Ooh, yeah. Just add zeros.
I'm thinking you were talking about our advanced students. I'm hearing a great extension activity. Give them the shortcut language.
Ooh.
And explain why this is not going to work, and then deeply unmask what maybe the most concise way we could say it that's actually true.
Sure. There's a balance though, right? Between like precise and concise. We put those words up on the wall in my classroom, like absolutely. Like I want precision and I want conciseness because I don't want it to be this lengthy, like, let's explain powers of 10 in a paragraph. Like, no, that's not how we do it.
No, and that's the least way to get a student to raise their hand and ask for help. They know you're going to come over and spout off a paragraph.
Right. Here, let me give you the 10-sentence explanation of how this works. But I really think if kids can see good examples of those things, and like you said, build that as an extension activity, make them write that language. And then I would bring it back to the whole group and say, okay, Sally's got this definition and I'm excited to see what you guys think about it.
Is there anything we could tune up in the language?
Pressure test it. I want some of you to find other examples. Like, is she right? Is she right all the time? Is that true in math everywhere? Think of other numbers. Throw your fractions in there. Does it still work? Like, does that theory still make sense?
And you mentioned putting stuff up on the wall. I'm like, could we put these like, don't say this up on the, like maybe if Sally did like come up with an amazing product,
sure,
let's get it up on the wall. And
absolutely. Anything they definitely like come up with, theorize, or that sort of thing. Exactly.
Do you have any other big examples of imprecise math language that you hear that you're like,
oh man, they're good, man. I'm trying to think because it's funny. You almost come across them randomly. And then you're like, wow, have I always been saying it like that? I'm trying to think of others, but
I'll introduce one.
Okay.
So fascinatingly, in my opinion, when we introduce the number line, we always introduce the x-axis.
Okay.
Like left to right.
Sure.
So kids start getting really attached to like the right. The right is the greater magnitude, right?
Yes.
Now I'm scared. But what's so interesting to me is that in my opinion, the best way to introduce the number line is the y-axis. Yeah. Because students intuit up and down because we have gravity. Mm-hmm. But I mean, where do we invent this whole right versus left?
Right and left, because on our wall, there's only so much space above the whiteboard that the number line has to go across this way. You can't go
Mystery solved. Mystery solved. But I think that the imprecise language that we're lending towards is that like, you hear students being like overly attached to like, well, it's to the right.
It has to be this way because that's the rule I memorized. Right.
And then when we introduce, the X and Y axis and it's like, well, it's really up and to the right. Mm-hmm. Like, I feel like having kids exposed to multiple modalities then opens the door for them understanding why that language was maybe limiting. Maybe not imprecise, but just limiting.
Right. They can see outside or beyond their perspective. And they like that too. If you're like, by the way, this is next year's math. They're like, oh, we're learning middle school math. Yeah, exactly.
Well, and asking them their preference. What makes more sense to you? Raise your hand if it's the left to right number line. It's the up and down number line.
Sure. Now, let me give you an example where you might need to use, both or something like that. And think of when we get to integers, man, everything's in sixth grade.
Right.
You taught sixth grade, right?
I love it.
So it's like that key year of just like, remember how we said all your numbers live on this side of zero? Now there's an infinite number on the other side. And it's just like, what?
Welcome to sixth grade.
Holy moly, you just doubled infinity. How did you do that? And so, but if you think about those contexts where we say elevation, like sea level, does it make more sense for me to plot a change in sea level on a horizontal number line versus a vertical?
We talk about it all the time.
Exactly.
Well, and then we talked about it like when I introduced negative numbers and we talked about it being like a building, like an elevator.
Yeah.
And if it makes sense, what floor is the lobby on? Is that L or 0 or is it 1? And like talking about like, well, do buildings have negative, like can the elevator? Yes, there's a parking deck. And so like having them kind of like argue about that, but really making it visual. You're right. They would never illustrate like the height of the elevation of a volcano the elevation of a volcano on a horizontal number line.
Yeah, it absolutely makes sense. You know what's funny too is we wait till sixth grade to talk about those negative numbers,
right?
Because the standards tell us wait till sixth grade to do that.
But they're intuiting it far before that.
I've played with it with second and third graders, and they can understand and intuit what a negative number is and how it relates to a positive number.
Yeah, they can intuit borrowing.
See, that's the thing is we kind of get to the end point. We're like, well, they have to be able to add and subtract them. It's like, no, not yet.
No.
Like, what's wrong with saying like, okay, so we're always talking about these numbers that are like greater than 0, but what's on the other side? Like, ask a second grader that. See what they say, because they may be able to come up with one of these contexts. Like, I remember being in this building where there was a B1 button on the elevator. I didn't know what that was, so I asked. And, they could tell you this whole story about how they discovered something less than 0, and how authentic is that, right?
But it's like we can't even start worrying about imprecise or precise language until we start inviting that kind of like you're almost like talking about intuitive math.
Yes.
And like Of course,
Absolutely.
intuitive math is going to have imprecise language.
Because it's messy.
Right.
We have to start messy with
Because
it.
with our feelings, like we kind of feel math before we learn it.
And we have to invest ourselves in it. So I think it has to affect you if you're going to have any real like connection to it.
What are some strategies that you have for supporting advanced students in the room? We talk a lot about how to reach those students who might be struggling, especially as they arrive to us with serious gaps in their knowledge. But what about, because that does dominate our attention, what about the advanced student? What do we do?
Exactly. I love that we're having this conversation, by the way, because so much of that focus gets sucked to, those kids who need more support. And rightly so, right?
Yeah.
Like they definitely need the support too, but I'm a firm advocate of advanced is special ed too.
Wow.
They are absolutely the same type of kid who needs special attention. And it's actually my story. Like I grew up in gifted and talented courses, right? But got to this level of just not really trying, not really being interested in, not having, a teacher who would kind of press on me to go beyond what I was putting out, right? So if you think about in your K-5 experience, like to be an advanced kid in math just meant you could regurgitate your facts really quickly because teacher puts the problem up on the board. You're like 17,
you see it.
Done. Now I'm sitting here like spaced out, not interested in anything else because I got it the fastest of anyone in the class, right? But because that was my goal. And then that's what it like felt like to be advanced. But it wasn't until I kind of even got to high school and maybe even beyond that I found a love for mathematics because there's so much more to explore when you get beyond like, I'm just fast at it, right? And I think we often like confuse those two things of like fast at math and good at math. Those aren't the same thing.
Precise language.
Here we go. Another soapbox, but it's absolutely adjacent to the precision of language because we look at a kid and, we're saying, all right, so when I'm asking these questions of the whole class, you're always like, bam, first one to answer these things. Like maybe you need to be on the advanced math track, right? And in 5th grade, if you're computationally fluent, you absolutely look like you know what you're talking about without having to actually justify your thinking a lot of the time. So we put you in the advanced track. You may or may not struggle as we get into these deeper conceptual things. But I think the most you can do, so getting back to your original question, for an advanced student is press on them to justify their thinking. They need to be the ones who are absolutely backing up every argument they make in mathematics. And then they need to also be the ones focusing on the thinking of others and critiquing it because they need to help others find the holes in the arguments that are out there and give an example that would break that theory.
Yeah.
So that then we can kind of build this classroom of like, wow, there's a lot of give and take here to get to that great idea that's at the center of everything. I think another area, I wrote a blog post that's going to get published here pretty soon on Teach, Learn, Grow that's about proficiency in mathematics. And we kind of see it this way in K-5 of like, if you're fast, then you're proficient in mathematics, but kind of refocusing that on an idea where it's not a race, it's not who's the fastest, but there are actually 5 strands of mathematics. And so one of them is computational fluency, and that's great.
Yep.
That's one leg to stand on, but there are others, right? Conceptual understanding is one of those. Adaptive reasoning is another one of those. Productive disposition is another one of those. And so because of that, I think advanced students get really far down this trail of computational fluency, and then their adaptive reasoning and their conceptual understanding kind of starts to falter. So I think we can do a lot more for those advanced kids to make them model their thinking. Like if you ask students, like they solve the problem really quickly, right? And then you tell them to go back and can you draw a model that would help this make sense to everyone else in the room? That might be a stumbling block for them. That might take them back for a second because but I did it. See, I put the big number on top. I did the subtraction.
It's always 7.
It's probably C because this is just, we're going to take the test on this.
Right.
And they got the answer. And that was the whole point. And so reframing even their language of how they talk about it as it's about the journey. It's like the thinking of how you got there is way better than the answer. And oftentimes when I was teaching, we'd get to the end of the problem and I'd be like, okay, let's move on. And they'd be like, but wait, was that the right answer? I was like, who cares?
And also, why are you asking? If you're this fast, you should know.
Exactly.
But also,
Or you justified your thinking throughout the whole thing. So you tell me, is it the right?
Right.
But they just want to be validated that like that end point was the whole goal. It's like, no, buddy, the whole time was the goal.
Yeah.
Your thinking through all of that was the entire focus of this activity.
Because they're going to get bored. They're going to be so bored in math. It's going to have the exact same effect as our learners who are on the most struggling end of the spectrum.
Yeah.
Checked out.
Right.
They're going to check out. And I think it's really important to notice, though, that when you ask that kid to draw a model and they struggle, and they're sitting next to a student that maybe isn't quite as computationally fluent,
Sure,
or is maybe a little further behind, they're going to be the one that is like, why are you drawing it? Like, no, just here. And they're like,
yes.
And then that's where they shine.
So this, and you went right into it. So this is exactly what my blog post is about, right? It's perfect. It's almost like it was scripted. No, that part definitely wasn't. And this is what I talked about, is where if we start seeing proficiency in mathematics is multidimensional instead of just the score you got on the last big test, then everyone has a chance to shine. Everyone has an area where they are stronger. Then that affects how you group students, right? Like random grouping's great. Ability grouping, you got to be careful with, because you don't always want your
you don't always want everybody with everybody. Yeah.
But maybe if I identify you as someone who is really good with the conceptual understanding and can explain the big idea, like how does this relate to magnitude? I've got 3 kids who are good at that. Okay, we're separating you guys into different groups so that your whole group can benefit from that.
I saw this a lot in my class.
If I've got kids who are great at drawing models, spread them out.
Yeah.
And it is, you know who it is? It is those kids who need more support, because that's where their focus is. They're constantly being drawn back to those concrete and pictorial models.
That's right.
Because that's where we help them the most.
And they might not be amazing at drawing it, but they are going to be very good at evaluating. They're going to be going,
yes.
But when you put it like that, I think it's this.
So then they're powerhouses in those groups where you'd think the advanced kid would be leading the charge. And you're like, well, no, I'm only interested in the model. How would you model this situation? Then they have to rely on each other to get to that point. And it's a great moment for that, right? When your student who needs the most support goes, I just did that. Crushed it.
And
Absolutely.
then your advanced student is like, can you help me, kid?
Yeah.
Can you help me, buddy? Can we Batman and Robin over here?
Yeah.
Aaron, thanks so much for coming on and talking to me. I'm going to ask you one final question.
Absolutely.
What is your why? Why do you teach? But why are you a nerdy researcher?
A nerdy researcher every day. I think there's a long way to go still. And I guess that's what got me interested in education in the first place, is like, we're not done finding the best way to do all this stuff. We can come to conferences and there's a new revolutionary idea every year, right? Maybe it's an old idea that we're rebaking and it's like, wait, that's a novel thought. But there's always something more to be learned about how humans learn. And there's something about that that's so like enticing and attractive to me. I just love watching learning happen in other people. And obviously, I'm pretty addicted to it myself. So I think that's why I'm here.